Hello, everybody, and welcome to the 2022 edition of INSPYRE, the International School on Modern Physics and Research, organized by the Frascati National Laboratory of INFN, the Italian National Institute for Nuclear Physics, and addressed to high school students attending their last 2 years. I'm Pasquale Dinezza, a senior researcher at the Frascati National Laboratory, and I will be your virtual host for this first day of lectures. So it's a pleasure to start with welcome of our director, Fabio Bossi. So please, Fabio.
Okay, good afternoon, everybody, or maybe good morning, good night, I don't know. Since this is a virtual meeting, probably people can connect from everywhere in the world. So it might be a different time at your place. This is a very nice occasion to say hello to many people coming from many countries, and this is particularly relevant in these sad days of war. We will talk about nice things instead during this school, our science, which is besides being a beautiful argument, is also an argument which makes people stay together in peace and collaborate. So this is very important, specifically these days. I must confess you that just a few minutes ago, I was overhearing the speakers of the next hours about they were chatting about what they are going to present. There are very exciting topics. It's particularly exciting. I would very much like to be a student to follow these lessons, because they will introduce in many of the puzzles, the mysteries, and also what we have understood about nature around us. This is the spirit of this school. This is the spirit of our field in general, to really try to understand as much as we can the beauty, the mysteries of nature. So we will not spend very much time, more of your time now. I think that what is interesting is to follow the next presentation. I am pretty sure that you will enjoy them, and hope to see you in person in the next years, maybe as a scientist colleagues. This is also the reason for we organize these schools, to let you understand what is the beauty of our job, of our mission, I would say, and so let's hope for the future. Thank you very much.
Thank you, Fabio. Now we can welcome Catalina Curceanu, who is the director of the INSPYRE School. Please, Catalina, go ahead.
Thank you very much, Pasquale. Thank to all of you guys who are connected. I see somebody of you already left us some message in the chat. Just write us, where are you connected from? And as you have heard, I am the director of this school, and I would like to welcome you to this edition 2022, which we would have been very happy to host you in person. I hope that next year this will be possible. So you might have seen that the title of this edition is Going from Particles to the Star, and we hope that we will bring with us in an inspiring adventure. Let me make you some introduction to this school, which is just starting today, and welcome you in many languages which I could find on the web. So I really welcome to all of you guys who are connected. Basically, at least you are registered from many countries in all the world. And this is our poster. It's an online edition where we try to put together an exciting program for you to follow these days. And this program, it's bringing you from the particle adventure. Actually, the first talk after mine, it's about one of the basic ingredients of the nature and also on ourselves, actually the proton, just to give you a hint that also there is still something to discover, up to the stars. So different type of stars, to go and try to understand the universe. That's what we are trying to do. And we will try to explain you how we are doing this. Just to give you an idea where are we talking about. So we would have liked to host you here in presence. This is the Laboratori Nazionali di Frascati in near Roma. And this is our lab seen actually as a very nice view. And one of our key ingredients is developing accelerators. And we have here an electron-positron collider. You will have a talk on this. That's one of our points of being proud. And we will tell you something about the research which is being done in this complex of accelerator, because it's not only the last part of the accelerator, but actually it's a complex starting with the LINAC. And we are developing other type of accelerators, and we are performing research in the beautiful town of Frascati, which is about 20 kilometers far from Roma. And we will introduce you all this. Oh, meantime, I see many of you are greetings from all of you. So hi, everybody. Hi once again. Write us again where you are listening to us from. Good. So this is the lab. Actually, if you see my arrow, I am now in this office. I'm talking to you from this office, which is quite nearby the particle accelerator. That's a very nice view of this accelerator, again, taken from outside, where many experiments have been done in the last 20 years. And I'll introduce to you in a lecture I will give on Wednesday. And that's the picture from inside. It's a complicated machine. It's a beautiful machine. All this physics which allows us to understand the enigmas, the mysteries of the particle worlds, but also in the aim to unlock what it is even higher, so going towards universe, neutron stars, and hoping to unlock the secret of black holes. It's something very exciting. Up to 2019, we were hosting you guys here in Frascati. And this school has started more than 10 years ago. If I'm not wrong, we are now in the 12th edition. And I know that we have done a survey, and many of the participants to this school studied or are studying science. Some of them, at least those in the very first editions, are now our colleagues and are at their turn, they are researchers doing research in many, many different areas. And we were really hoping we could host you here, but unfortunately, at least for this year, was not yet possible. And I see, meanwhile, so Roma, Napoli, Verona, Romania, hello, Romania, Czech Republic, that's very nice to have you here, Ferrara, great guys. So keep writing to us. Good. And you were registered in nearly 200 young scientists, future scientists, I hope. 81 are coming from Italy. And 21, which adds up in 102 colleges and high schools spread around the world, are coming from all these countries you have listed here. So Romania, which we have seen in the chat together with all these countries, and also Czech Republic, we have seen in the chat. Write us if you are coming from other countries which are listed here, or even if they are not listed in this list. Perfect. And you have seen we have put together a very nice program, which, as I was mentioning to you, is bringing you in a discovery of ingredients of matter, of like the proton, of the tools we use to discover, like big machines, accelerators. And also we will make an inquiry of physics underground tomorrow, illuminating the dark. And also from the dark, from underground, we will go through the accelerators again to the neutron stars. And again, physics, it's basically an experimental science. So we also want to bring you towards the next frontier accelerator, which will happen Wednesday, and also give you an overview of quantum technologies, which is something your generation will probably master pretty well. And Thursday, on 7th April, we will make an inquiry into mysteries of the universe, like gamma ray bursts, this very interesting phenomena involving huge quantities of energies, and also make an overview of the present James Webb Telescope, which is just now starting its huge, big adventure. And in the last day, even if you are not here physically with us, oh, hello, Luxembourg. Nice to have you here. Hello, Rome. Hello, where was it? Potenza, Venice. Hello, everybody again. And just because we wanted to have you here, also somehow in person, at least virtually, we shall make Friday a virtual tour in our visitor center and show you somehow how the experiments are working. And with this, we hope that you will come back in person sometime and visit us, as our director was saying, as colleagues, why not, or as just visitors. And that's a picture from inside the visitor center where we will bring you Friday. And one other thing, please make a screenshot on this. You also have it on the website. We are organizing a competition. And this competition, which has a deadline in about 1 month, it's 8th of May, it's kind of it's a kind of premiere for us. So it's the first time we are doing this. So INSPYRE 2022 contest, where we would be happy to receive from you feedbacks and insights in different type of forms, like short videos, presentations, articles, comics, drawings, whatever it's your way of expressing your creativity, and send to us your product at this email address. You see it here. And within the end of May, we shall do a committee and we shall award 3 prizes. So please participate. This is the first time we are doing this. We want to put this together and get a kind of inspiring in turn. We would like to be inspired by you from these very nice products. Again, hi again, Romania. Hi Caserta. It's nice to have you here, guys. Good. So did you take a screenshot? I hope so. So we will wait. We will again tell you these days about this, but yeah, we wait you to participate to this. And approaching the end of my welcome, I want to repeat that science has no borders. It's the best example I could imagine, of course, together with art, to interrelate people to progress and to peace, which nowadays it's so much important. And our school is also organized in the sign of science for peace. And having said this, and having also thanked to our supporters, which are the Tech European Project, FQXI American Foundation, the Strong 2020 European Project, and the John Templeton Foundation. So after having said this, I can only conclude to thank a lot from all my heart to all the people and the team from the Education and Public Outreach Group led by Susanna Bertelli, whom you see here in the middle, together with Sara Reda, Elisa Santinelli, and here we have Sara Arnone, Deborah Bifaretti, and Elena Patrignanelli. So thank you, huge thank to you, team. And having said this, I conclude my introduction and I welcome again to all of you. And yeah, you can attend the contest in couple. You can do whatever you want. Just express yourself. You can do mini groups and whatever you want. Good. So thank you very much, guys. And I welcome back Pasquale to lead, to chair the first day of our INSPYRE school. Thank you very much.
Thank you, Catalina. Thank you for this nice introduction. Okay, so now it's time to start our first session with a lecture devoted to one of the most famous particles, the proton, and in particular its radius. The webinar is held by Professor Jan Bernauer and Professor Randolph Pohl. Jan Bernauer is professor of experimental nuclear physics at the Stony Brook University and worked on proton form factors. Now, in particular, he works in international experiments like MUSE, Dark Light, S-Phoenix, EAC. Randolph Pohl works on laser spectroscopy of hydrogen exotic atoms at the Max Planck Institute of Quantum Optics in Garching, Germany. And the webinar
at the University of Mainz now.
Oh, sorry. Okay,
no problem.
Okay, the webinar will give us an overview of what has been done so far in the investigation of the proton and which are the perspectives. I remind you that you can write your questions in the chat, and in the end, we will try to answer to some of them. So, Jan, Randolph, the floor is yours. Thank you.
Yeah, thank you very much for this introduction. And yeah, welcome to this international talk. Right? Randolph sits in Mainz in Germany, my own old hometown. I'm now in Stony Brook, something like 60 miles east of New York City. All right, so today, how big is the proton? This is really a modern puzzle. But we know about the proton actually for some while. Right? So the proton has been discovered now 100 years ago, more than 100 years ago by Rutherford. And we actually quite early learned that it cannot be an elementary particle. Like Stern found that it has an anomalous magnetic moment. So that means that it has some quantity which cannot be that value if it's an elementary particle. So it must have internal structure, and if it has internal structure, it must have a size. It can't be point-like, right? So it must be some object, some sizable object. And after that, we learned how to describe what's inside, and that's quantum chromodynamics. Right? Essentially, all visible matter is described by quantum chromodynamics. In fact, most mass is created by quantum chromodynamics. You have heard maybe about the Higgs, which gives mass to the elementary particles, but the mass you see around us is actually generated by dynamically in the nuclei. But it's a really hard theory. It's not easy to calculate. So we really want to understand at least the simplest stable system. That's a proton. That's the simplest system you can just put on your desk, right? As in the form of hydrogen gas. And one elementary question of that is, how big is it actually? So when I did my PhD in Mainz, actually, on the proton, we measured the form factors. That was in part of the A1 collaboration. And that was actually not aimed at this proton radius. What we were looking for were these form factors which describe how the proton, or how much the proton is not a point particle. Describes how the charge and the magnetization is distributed inside the proton. And if you look at earlier data, so we are not the first one to measure this. If you look at earlier data, you can see that there's, if you plot it the right way, that there is some kind of bump. And we want to measure that bump. Right? I won't go into too much detail on that, but that was the original motivation. And now we go to Randolph.
Okay. Yes, thanks, Catalina, and thanks, Pasquale, for the invitation, and thanks, Jan, to let me continue with this talk. So Jan is doing form factors, and I'm doing something completely different. My group is looking at atoms, and we do laser spectroscopy of atoms. And as you will see in the end, these two very different fields, accelerator-based form factor measurements and precision spectroscopy of atoms, they come together and they focus on the point of how large is the proton. So you know that atoms have a nucleus, and this nucleus is orbited by electrons, okay? And this is also Rutherford's picture. The nucleus consists of protons and neutrons, And the hydrogen atom is the simplest of all atoms. It just contains one proton, and we know it's extended, and we want to determine how large it is. And in the hydrogen, there's one proton orbited by a single electron. And as far as we know, the electron is point-like. And so by looking at the precision spectra of this hydrogen atom, we hope to be able to determine the size of the proton. Now, you all have probably heard about this Bohr model of the hydrogen atom, where you have this one positive charge in the center and the electron going around. And Niels Bohr won the Nobel Prize for explaining the hydrogen spectrum measured by Rydberg, and he got this beautiful Bohr model. And what you have to know from the Bohr model to understand what we are doing in the experiment is that you have discrete energy levels, which can be seen here. You have the center. In general, this is a Z times plus elementary charge for a nucleus with charge Z. And then you have different energy levels, and these are discrete energy levels. And the electron can be on any of these levels, but not in between. And you can make the electron jiggle around between one of these states and another one of these states by letting it absorb a photon. Or what is depicted here in this Wikipedia picture, if the electron falls down from a higher level to a lower level, it emits an energy. And the energy of this emitted photon is exactly given, or the frequency is exactly given by the energy difference between these two energy levels. Okay, so you have discrete orbits, and you can make quantum leaps inside such an atom. Now, a hydrogen atom is very tiny, and the proton is even more tiny. So if you blow up the hydrogen atom, that it has the size of the Maracanã Stadium, then, so if this is the electron orbital size in a hydrogen atom, then the proton size is as small as the ball on a small needle. So imagine that you can do spectroscopy and looking from very far away from the higher ranks of the Maracanã Stadium towards the proton, which is like this needle in the center of the football field, and trying to determine this with great precision. But that's what we do, okay? Now, these quantum leaps, you can also understand that you have distinct seeds of rows of seeds in which the electron can move around. So that is also somehow how you can imagine the Bohr model of an atom. Now that I've convinced you that the hydrogen atom is a nice, simple system, I have to tell you it's all wrong, right? This was a lie. It's a good picture in some sense, but in reality, an atom is not a planetary system. There are not such fixed planet-like orbits. Instead, you have to invoke quantum mechanics, and you have to talk about wave functions, and you have to talk about probabilities. That is, where do you have a possibility to find the electron in the space around the proton, okay? Now, if you do then quantum mechanics, and the simplest part of quantum mechanics is maybe this picture, you get these different Bohr energy levels, but then there are more levels coming up. And this is even not the full story. There are many, many more levels in hydrogen. But what we need to know today is that there's this ground state, this what we call 1s state. Then there's this first excited state, which is the 2s state. And then there's the 2p state. And what I plotted here is the probability to find an electron somewhere around in this 2s state and in the 2p state. And what you realize, there is a small dot in the center. This should be our proton in hydrogen, okay? And in fact, for this 1s state and for the 2s state, there is a maximum of the probability to find the electron exactly at the position of the proton. And in this other state, the so-called 2p state, the probability to find the electron close to the proton is 0. And that is what we need to know. And we also need to know this term called lamp shift, which is the energy difference between the 2s and the 2p state. Here's again this probability. So the probability for these s states in this as a function of distance from the proton is maximal for this 1s and 2s states. Now, this literally means that if you look, where do you find the electron in such a hydrogen atom? The highest probability is to find it in the center of the proton. Right? The proton is mostly empty. There are a bunch of quarks and gluons. This is the QCD stuff that Jan was talking about. And there's a lot of empty space, so the electron can actually go inside the proton. And when it's inside, it is not attracted anymore by the positive charge of the proton, because the positive charge of the proton is all around it. And so on average, there is no attraction for a short moment in time between the proton and the electron. And that shifts this energy level, this S state, a little bit upwards. And that shift can be determined by experiment. Okay, so this was the excursion in theory of hydrogen atoms. The rest will be easy listening. If you have questions on this, just send me questions. This 2s to p energy difference, this so-called lamp shift, was discovered in 1947. And in the previous theory, this 2s and the 2p state, so these two guys here, should have exactly the same energy. But it turns out that they do not have the same energy. And the reason is vacuum is not empty. There's always particles and antiparticles inside the vacuum which occur and then they go away again. And then also the proton charge radius shifts the S state, as I told you before. And the observation of this energy difference between the 2s and 2p state was a disruptive event in physics. It did not follow the Dirac theory, which was believed to be the correct theory for all our universe around us at that time. And it motivated the development of quantum electrodynamics, which is today the best theory that we have to explain everything around us, like atoms and why do cell phones work and how do stars produce light. Okay. So LAMP measured something, and theorists calculate this, and I would like to give you an impression about the difficult work that theorists do. I showed you the picture before where you see these energy levels of the 1s state and 2s state and so on. And if you look at this Bohr model, you get out that the energy is proportional to 1 over n squared, where n is the principal quantum number. This is just a number. Now, Dirac put special relativity into the game and got a nicer, a longer equation. But then the real work started, right? Then people started to do quantum electrodynamics. And what they come up with in the last 50 years or so is a really huge expression where you see corrections and smaller corrections and even smaller corrections. And then when you continue to look at what these brave theorists have calculated over the last 50 years or so, it's really, really complicated. And in the end, when you do all this fantastic theory, it fits with the experiment on the level of 12 decimal places. But you see here, these terms in the bottom, there you see this RP square. This RP is the radius of the proton because the nuclear size also affects these energy levels. And if we want to test the calculations and understand if quantum electrodynamics is the end of the story or there may be new forces in the universe, then we have to compare this theory expression with the experiment. And if there's agreement, then QED is good. And if there should be disagreement, then we have a problem. So in the end, what we have these energy levels, which we measure in hydrogen. And then we have a theory that is this complicated thing I just showed you before, and that depends on a number of parameters, in particular on the proton charge radius. And with that, you see that the proton charge radius, which was determined by electron-proton scattering in previous years, had to be plugged in to test QED. And in fact, it turned out that the proton charge radius from electron scattering, when Jan and I met for the first time, was not good enough to exploit the full accuracy of the measurements. So we needed a better proton radius. And you could then turn this around and say, let's determine the proton radius from hydrogen by believing this theory and believing the calculations and the measurements. And then you solve this equation for the proton radius. And this is this point that you have here. So if you believe QED, then you get a proton radius from hydrogen spectroscopy. You can take the electron-proton scattering value, which at that time had a larger error bar, plug it in, and then there's agreement. But of course, we want to test this on a much higher level of accuracy. And that's where Jan came into the game when we've met for the first time in Italy.
Yeah, exactly. Yeah, so we met the first time in... I have no echo. So we met the first time in Italy, close to Venice, at the PISA's conference. And I wasn't quite sure why I was invited there. It was actually on San Servolo, which is a small island there. And when I arrived there, I learned that this was an insane asylum for 250 years. and then it made all sense. Anyway, so Randolph was there to talk about his non-progress in measuring the proton radius with his muon experiment, we will talk about in a minute. And I was invited to talk about the Planck scattering measurement, right, of this bump. But there I actually learned that Savely, the organizer of that conference, kind of has given up on Randolph because it took so long. So his goal was to convince me to actually extend our experiment to also aim to measure the radius as well. And then that's what we did. And to describe it a little bit, how we can actually get the size of the proton out of scattering, I have this analog here. I always say, well, what I'm doing is like playing billiards, just with much smaller balls. And it's a little bit of a stressed picture, but actually can give you some idea of what's happening. So normally, if you just shoot the ball on a target ball, it will go off at some angle, depending on where you hit it, right? In that moment, you transfer momentum to it, right? Some momentum from the projectile to the target. And you can see where the target goes. Right? When we do that with protons, it's essentially like we're doing this on a very large table, right? So you don't know exactly where the balls are. You can't see the balls. You just see where they go in some sense. And we can do that many, many times, and we will hit different parts of the target, right? So we will see it go away in different directions. You don't quite see it in the slide, but I mean, you can imagine, depending where you hit, right, it goes off in different directions. And we do that with many projectiles at the same time. Most of them, actually, essentially all of them, will just go through your target, right? But some of them will hit the proton, and then they will scatter off. And if you look very closely, actually, it's not a hard scatter like if you have two billiard balls which touch and then scatter off, right? The proton has the size, and it's a cloud of charge in some sense. And it's attractive. So actually what happens if you look close by, they will swing by each other like you see it here. And depending on the energy of the electron, on the distance where you shoot it, you can enter this cloud. So from that, you get some idea how information about this cloud goes into the angle distribution. We don't know where they are, right? We only really see the angle in the end. So we can shoot a lot of balls. We don't know at what distance we hit. We only know how hard we shoot, and we can see where they come out and with how much energy they come out. And we can record that and just get the statistics. How often do we see certain angles? And that will be different on depending on the shape of the proton. You can see that here in this video. So there are two different charge distributions hidden here, right? And if I scan through this, right? Assuming I could actually scan this, not just randomly shoot at it, you see that I get different statistics, right? One of them has more of the small angles and then has a really extended angle range, but the other one has more of the small angles. And that gives you can convert that back into the size of the proton, and actually not only the size, but the whole distribution of the charge. Our Q sticks are a little bit different, right? We have to use an accelerator. This is, for example, the Mainz accelerator, MAMI. We have different stages. So the beam starts here and goes into this racetrack microtrons. RTM3 is the biggest one. And then we can either use the HESM, that's the last stage, or directly go into our hall. And this is the A1 hall, where we have the detectors on the target. This is how it looks like. Just to give you an idea how big this is, this concrete block is about my shoulder height. And so this is about 3 stories, right? These are all magnets. The beam is actually in this thin aluminum tube, right, in vacuum. The target height's somewhere here. You can actually not see it right now. And we can move these 3 big spectrometers, 200 tons plus, around on this ring here that's covered by this black covering. It's a iron ring, and you glide on an oil film. It's actually quite impressive. If you decouple the motor to drive them, and if you pump up the oil film, you can actually push them with your hand very, very slowly. The biggest problem is actually making them stop again. But you can do it by hand, 200 tons, right? But normally it's a small motor which moves them around. And we can go to different scattering angles and then record the particles. They are scattered off the target here, go through the magnetic system, and are bent into the detector here. And when they get out is what we call cross-sections. And just to give you an idea what that is, because it actually has a meaning. So this is an example for a scattering, right? And what we are actually looking at, or trying to measure, is if we look in the direction of the beam onto the target, we measure the area, that's the orange part here, which scatters to a certain solid angle, right? For example, the acceptance of our detector. And if you place it at different parts, it will be a different area and a different size seen from this direction. That's the cross-section we measure. And going from there, we can say, okay, we have an idea of what that should be if it would be a point-like particle only with a charge, right? And then for heavier nuclei, we have to modify this by multiplying some function on it. Because of history, that's f squared. For the proton, it turns out we actually need two of these functions. One for the electric charge and one for the magnetization inside the proton. So that's GE and GM. And they have some constants next to it, some kinematical constants, which change depending how hard you shoot and from what angle you look, essentially. So in the end, we get these two distributions out. And that's actually what we are measuring, right? So we're getting out the distribution of the electric charge and of the magnetization inside the proton. Parameterized not as in distance from the center, but in this q square, which is the magnitude of the pulse you give it. That's the magnitude of the hit for momentum you transfer. In the end, we can actually define a radius like this. So we get the charge distribution out and the slope of that charge distribution in the limit that we didn't touch the proton at all, right? That we have we just go pi, right? No momentum transfer. The slope of that function, that is the radius squared. That's actually what we measure. And that's actually also what shows up in Landau's formulas. So to give you an idea, right? So we measure points along this q square, and then we have to fit somehow, right? You can't measure at 0 because then nothing scatters. Can't distinguish this from not scattering because there's nothing there. You have to extrapolate and find the slope of it. And that gives us the radius. And we have done that in that Mainz experiment, right? And I really want to thank the L1 calibration. I couldn't have done it without them and my advisors of that time to get this large data set. It's actually, at that point, was 6 times the statistics of the complete world data set. 1422 data points. You can see that here, just plotted, and they have some shape. And that gives you the distribution. All right, back to Randolph.
Yes. So when Jan showed his results, they were in perfect agreement with the value that was previously determined from hydrogen, and that improved on the previous world data by a factor of 2, as he just said. And everything seemed to be in order. But you see, despite the gigantic efforts of this beautiful experiment that Jan performed in Mainz, the error bar is still rather large. And you would like, in order to be able to test QED at a more precise level, you would really like to have a better proton radius. So we can push the test of our best models, of our best theory models by, say, an order of magnitude. And so our goal when I did my PhD was like 25 years ago or so, was there's an idea how to shrink this uncertainty by a factor of 10, which is, of course, very difficult, okay? And the reason why we believe that this should be possible is not because we're so much better experimentalists than everybody else in the world, but because we use a different system. And now I introduce you to my favorite particle, or the piece of matter, which is called muonic hydrogen. It's a hydrogen atom, so it is a proton at the center, but this is not orbited by an electron, but by its heavier brother, the so-called muon. So what is the muon? The muons are basically heavy electrons. Their mass is 200 times larger than the mass of an electron. And they were discovered in 1936 by Carl Anderson and Neddermeyer as a part of a cosmic radiation. If you stretch out your hand at sea level, you have about 1 muon per second per hand going through your hand, okay? That cosmic radiation comes from protons from the sun, striking the upper atmosphere and producing particles called pions. And these pions actually decay into muons and neutrinos. And this happens very high up in the atmosphere. And the muon lives only for 2 microseconds. So in fact, muons shouldn't even arrive at the sea level. But because of time dilation of Einstein's theory of special relativity, the clock ticks slower for this moving muon. And so it can still reach the ground where we can measure it, despite its very short lifetime of only 2 microseconds, so 2 millionths of a second. This was a major discovery in 1936 because at that time we had a very beautiful standard model. Our standard model at that time was we have protons, we have neutrons, and we have electrons. And that was everything you needed to explain the matter around us. Okay, Anderson had gotten the Nobel Prize in that year for the discovery of the positron, which is the antiparticle of the electron. So there was probably some hidden symmetry everywhere, which is nice for theoretical physicists. But in the end, everything was nice and fine, and you could explain everything with the proton, the neutron, and the electron. And then there came up this muon, and it was not. It was a new particle, which was not in anybody's mind. And when Rabi heard about the discovery of the muon, he said, "Who ordered that?" Because it didn't fit anywhere in this beautiful idea of what matter is made up from. And today, of course, we know where the muon is, right? So this is our standard model of particle physics. And here you have the up and down quarks, which are the main quarks inside a proton. The proton is 2 up quarks and 1 down quark as a valence quarks. And in the first family, there's also the electron, which is the particle that makes up the atoms together with the protons and neutrons. Neutron is also up and down quarks, but the other way around. And here in the second family, in the second generation, there's this muon, and there's even a heavier counterpart. It's called the tau particle. So we are dealing now with protons made from up and down quarks and orbited by a muon and not by an electron. The fact that the muon mass is 200 times larger than the mass of an electron means that the average distance between the muon and the proton is 200 times smaller in muonic hydrogen compared to the electron distance in normal hydrogen. So this is vastly not to scale, right? So if this is the Bohr radius, this is the Maracanã Stadium and the needle I showed you before, right? The muon is 200 times closer, okay? That's a lot closer. And because it's so much closer, in fact, it's closer in all 3 spatial dimensions, right? It's closer in X, in Y, and in Z, which means that the probability to find the muon inside the proton is 10 million times more higher in muonic hydrogen. So the muonic hydrogen particle or system is 10 million times more sensitive to the size of the proton. And that's what makes our experiment so much better in determining the proton charge radius. It's just this fact, okay? Good, so using cosmic rays for an experiment is not good because they are not so many and they are not controlled. So what we do is we go to an accelerator at Paul Scherrer Institute, PSI, which is halfway between Zurich and Basel. You all know this nice accelerator down here at CERN. This is not where we are. As I said, we are halfway between Zurich and Basel, close to the German border here. And this is our accelerator building here. It's the world's strongest proton beam. We start with protons to produce these pions, which is the thing that's happening in the upper atmosphere, and the pions then decay into muons, and these are the ones that we use. We get about 10 to the 8 or so muons per second from this accelerator, and this is of course much more than 1 per second per hand. This accelerator is located in a very scenic region of Switzerland, and here is the experimental hall. And if you enter the experimental hall, there's also concrete blocks. These are 2 meters high concrete blocks, and this is against the radiation. It's for shielding. And here in this barrack is where our experiment takes place, and the accelerator is hidden behind some concrete blocks in the back of the building. It's a really huge building. Okay, from top, you see these different beam lines. There are several beam lines. There's one beam line here in the first floor. Then there's There's a beamline which comes out here and continues there, and then there's other beamlines here. And this funny curved beamline here, where you see a close-up here, this funny curved beamline is where our experiment takes place. Here we start with protons, then we produce pions. These pions decay into muons, and these muons are then guided around and stopped here inside a huge magnet. And below this concrete, there's a huge laser hut where we produce lasers, because we do laser spectroscopy of this muonic hydrogen system in order to determine the charge radius. This is our laser hut. You see lots of colorful, shiny lasers. There's 532 nanometer green light. There's 515 nanometer green light, which is a bit more bluish. In the back, there's a gigantic infrared laser, which is a massive device. You have 2 kilowatts of light constantly shooting into a crystal, and then we take out pulses once we detect a muon coming in. And then in the end, we convert this light inside a huge hydrogen pressure cell, and then we go through a vacuum tube up here, and then behind the concrete wall into the area where the experiment takes place. So this was me, in younger years, where I was assembling the 5 Tesla magnet that we were using here. On the side, you see Franz Kottmann, who was the driving force behind this experiment, starting from his PhD until his retirement. He pushed towards laser spectroscopy of these muonic atoms, and finally, 10 years ago, so we managed to do this for the first time. This is what you saw from above. Okay, so here we have pions coming in, and these pions are stored in a magnetic bottle configuration, as it's called. Then these pions decay into muons and are slowed down, and the slow muons go around in this normal conducting magnets here in this vacuum tube here. This is a 2 by 2 meter concrete block, 1 meter wide. This is used for shielding, because you produce lots of gamma rays and neutrons and whatnot when you have pions entering such a material here. Here's the experiment taking place inside this 5 Tesla magnet, where there's a hydrogen target, and the muon slows down inside the hydrogen. And as I said, here's the laser hut behind this concrete wall, and there's later in this experiment, there's a laser beamline coming here and entering here. So we do the experiment here. Now we've made a movie how this looks, and I hope that this works now. So this is the artist's view of our setup. There's a yellow pion coming in and slowed down in the magnetic bottle, and now it decays into a muon. And this muon is running through a 30 centimeter diameter, very thin plastic foil. It's only 100 nanometers thick. And this does this a few hundred, like 100 times or so. And when it's slow enough, it's no more confined by the magnetic field from these coils. And the slow muons can leave on the axis of this magnet and then go around this concrete block that I showed you before into our 5 Tesla magnet. Now everything is a bit quick. The muon enters, and there are very thin carbon foils here, and muon kicks out electrons, which are then detected in this plastic scintillator here. Then the muon is drifted, and it does the same again here, and there's the plastic scintillator here. Now we know that the muon is there. Our laser is working. The muon makes a muonic hydrogen atom and is kicked by a shot of light. So this is the center of our target. This is an aluminum vessel filled with 1 millibar of hydrogen. This is the main difficulty in this experiment, is that we have to have muons which actually do not stop easily in matter, and you have to stop them at 1 millibar hydrogen gas over a length like in the size of a pencil, 20 centimeter long or so. And then you have to illuminate this from the side with laser beam. So the laser pulse enters here through a window, bounces from this curved mirror, enters a multipass cavity, laser cavity, through a tiny hole in here, and bounces back and forth between these mirrors. There's one mirror here, and there's another mirror there. And the muon, there's only one muon at a time coming in and making one muonic hydrogen atom at a time somewhere. But the light fills this whole volume, and no matter where the atom hides, it will be struck by laser light. And if it's on resonance, like I showed you in this Bohr model, you can shuffle the muon from one state to another one, and that produces X-rays in return. And these are detected by these photodiodes, these square-shaped things, which are the size of a fingernail or so. Okay. I said I started this with my PhD. Actually, there were people in the group who did this much, much longer, from the 1970s on already. We tried this for the first time seriously in 2003, and there was nothing. So we were looking for a resonance in this data set. So we wanted to have a big peak here. And of course, we had the prediction where to find this peak according to Jan's measurements and other measurements in electron scattering and also from the hydrogen spectroscopy. So we said we know how large the proton is. We just have to find this resonance peak. And when we find it, then we immediately improve the uncertainty by a factor of 10 or so. But for many, many years, there was nothing. And we were completely puzzled why we didn't see any signal. And then, in fact, the last time that we had the chance to do this, this was in 2009, we actually managed to find the resonance. And because it was quite exciting, I want to show you how we did this over 3 weeks of data taking. 24/7, so all around the clock, Sundays, Mondays, every day. Since I cannot bore you for 3 weeks, I've made a time-lapse movie of this, of the search. And so this is the spectrum where you would like to see a bump, a peak. And this is the prediction from electron scattering. And this is the prediction from hydrogen spectroscopy. So you would like to see a peak on top of some background somewhere there. And you see the Poisson statistics. We have a very low count rate for background. And you see these individual clicks that we record. We are actually basically counting X-rays over days and weeks of beam time. So you see that there should be some bump, and maybe this is it. We were a bit puzzled. Maybe there is some peak, but it's a bit small, but maybe it is this. But then we realized that we produce visible light in our setup, and our data acquisition takes it as a signal that we were looking for. And when we wrote some software to get rid of it, we were left with this, say, half resonance at the wrong position, and just in time for a long accelerator shutdown. So then we installed shieldings and improved the setup in a tremendous amount of work. And when the beam came back, finally, it didn't come back very nicely. When the beam came back, we could actually see that this bump also goes down again on the other side. So the resonance sits here, and it's far away from where it was supposed to be, right? It should be here, but it's 4 line widths on the side. And that means the proton is, in the end, is not the size that we had expected it to be, but it seems to be quite a bit smaller, a few percent smaller. Of course, only if nobody made a mistake, and if the theory is correct, and if the standard model is correct. So we then continued to measure this in hydrogen and also in deuterium, where we determined the charge radius of the proton and of the deuteron. This is the last plot that you saw. Here you see now a calibrated laser frequency. And this laser frequency can be calculated as a function of the charge radius of the proton. And if you put in the expected charge radius of the proton, this red peak should be here. But it's not here, it's on the side. And there's a calibration line from a water absorption line where we have very well-known absorption lines. There's one here, and there are several others here and here. So we can actually calibrate this frequency axis of the laser very precisely. And so our uncertainty is much smaller, but the central value is very far away from where it should be. Okay, so yeah, there we were celebrating. This is in front of the experimental hall, and we were having a badass party like physicists celebrate, right? We were sitting in the cafeteria, drinking a glass of champagne and eating chips and celebrating our great success. Actually, this road lasted for 12 years. It took us 12 years to come from the first proposal of this experiment to the result, basically because we've been looking in the wrong position for all of the time. We got quite a bit of response on our resonance. It turns out, according to our measurement, the proton is 4% smaller, and our error bar is a factor of 10 smaller than what people have believed so far. Here you see a proton size plot, and here you see this co-data and electron scattering measurements, which were available at that time. And laser spectroscopy in Munich hydrogen, our value is 4% smaller, and the error bar is much smaller. So this was quite some excitement. And And that happened in the 4 years between Jan and me first meeting in San Servolo in Venice until the next conference 4 years later, which happened in the French Alps in Les Ouches. And there we came together, and actually Jan's group had analyzed their data, and we had analyzed their data, but we didn't know about each other's results until this one day where we both presented our results. And it turns out that this is this 5 sigma discrepancy between the elastic electron scattering hydrogen spectroscopy, which agrees, and our value from Munich hydrogen. And now back to Jan.
Yeah, so what could have gone wrong? And so one of these experiments isn't right. So one of these results isn't right, or both. Right? Can't be right, both of them. So it could be in the theory, it could be in the experiment. And on the scattering side, the first question was, are actually our backgrounds and other experimental effects under control? And I will talk about that in a second. On the theory side, the biggest influence we have are radiative corrections. So the particle, right, if you saw the scattering picture, right, we describe it as a hard scatter, but actually there is exchange before that, right? Because it's an attractive force, this infinite reach, that changes the kinematics, and that you have to calculate this. And we do this, but maybe the theory has an error there. We have to extrapolate to 0. That could be problematic. There were a lot of papers written on that. And of course, it could be that there's some new physics hiding in there, something beyond the standard model, which changes the results, and we don't know about it, so we can't calculate it correctly. So initially, we checked our data with older data, and that showed very good agreement. Theory was updated, but that really mostly affects the magnetic radius, so the magnetic form factor, not the electric form factor. And there have been really tons of papers written on the extrapolation, and they really range from very good ones to very bad ones. But it's inconclusive. We really need more data at smaller q square. Yeah, and that's what we're needing. There were also a lot of papers about new physics. I would say there's no clear winner in the sense that everybody said, okay, obviously this is a good candidate. It's really mostly the people who wrote the paper who thinks that this could be a candidate, and everybody else thinks, no, that's not a candidate. But you never know, right? Maybe one of these papers is right. That would, of course, be, in some sense, the nicest result, because then we would have discovered something new. But in the end, when we meet, right, we meet regularly every 2 years or so to discuss the status of this puzzle. And the answer is always, we need new data to actually figure out what's going on. So Radolf will talk now about some new data. You're muted.
No, I'm unmuted. Okay. So this is an interesting result, right? So we have 2 types of experiments agreeing on the large proton radius, and one new kid on the block experiment being very far away from where it's expected. And so what do physicists do? You meet somewhere in a nice place. This is in Trento at ECT Star. And then you meet and you discuss. And the first time we did this was in 2012. We discussed the various aspects from theory and from experiment in all fields relating to that: atomic physics, nuclear physics, particle physics, people doing electron scattering, and people looking for physics beyond the standard model. So new particles, new forces. We had many talks in there, and then afterwards discussion sessions, which then became sometimes fighting sessions where people would, give provocative remarks, and then people started to argue back and forth and so on. And in the end, no conclusive picture showed up, right? So we had to vote, which is of course completely unphysical. But the majority of the people who voted thought it's a measurement problem, and it's not a problem of physics in itself, right? So that is what Jan concluded as well. We need more data. Okay, here you see Jan when he was young, and me when I was young 10 years ago or so. We had a bunch of follow-up conferences, and we will have another workshop this year. where we keep discussing all these various aspects, because there are so many ingredients. You could imagine that there is a part in theory missing, or we have not treated all systematic effects correctly in the experiment, or we're not talking about the same thing when we talk about the size of the proton, right? And so on. So all these things were discussed and I guess completely answered at these conferences, but there's maybe still something missing. So just to give you an idea of what could be, of what we have discussed, okay? So if it's a measurement problem, then either our experiment in muonic hydrogen is wrong, but we have a very small error bar, right? Or both normal hydrogen and electron scattering are wrong in the same way, which is a bit funny because they are not measuring the same experiment, right? But they are very well established methods of determining nuclear charge radii. Alternatively, the theory in muonic hydrogen could be wrong. We have a very simple and innocent looking formula, right? So the energy difference of what we measure is in some units 210 minus 5 times the proton radius squared. Of course, if there's any mistake in this formula, then we measure this side, but we would extract the wrong proton radius. So people have been looking into all these complicated QED terms that I showed you before in this movie where you saw lots of equations. And people have confirmed basically everything that was known at that time already. And then, of course, it could be an error in the standard model of particle physics that we have overlooked something in the particle. Okay. For example, people discussed if the proton looks different, right? We know that the proton is not a solid ball, but Jan told you that, this is a fuzzy ball of charge, and maybe the charge distribution is different. It's maybe not something like this, but it's, maybe some small center part and a very large halo of charge. That would explain the discrepancy, which was, there came out papers immediately the day after we published our paper. But electron scattering gives very stringent limits on this halo, and this cannot explain the discrepancy. Okay. Then, of course, one was wondering, maybe the muon modifies the proton, right? We know that the presence of the moon distorts the Earth, like the tides. The tidal forces distort the Earth. We have the tides, not only in the sea, but also in the land, right? So the solid ground lifts up by 0.5 meter or so, depending on the moon position. And of course, you would expect a muon, negatively charged muon, very close to this positively charged proton, should also distort somehow the proton. And indeed, this happens. And this is the so-called polarizability of the proton, because the muon polarizes the proton, right? It attracts the positive parts to its side and repels the negative parts of the proton. But this effect had been considered already in our funny equation that I just showed you, and it's much too small, right? So the discrepancy in these units of millielectron volts is 0.3 millielectron volts, and the polarizability is a factor of 20 or so smaller than what you would need to explain the discrepancy. Okay. For the experts, this is the Feynman diagram that we are after. This is the muon exchanging one photon with a proton, and you have the form factor in here. And you can also exchange 2 protons. This is what we would come up with, the proton halo, that muon would probe the halo of the proton. And the polarizability is if you have this proton in the center between these 2 photons, not being a proton, but being something excited because it's polarized, okay? So these Feynman diagrams had been calculated and they were included in our equation. So this could not be the solution. But then maybe it's a new particle, right? The standard model, as beautiful as it looks, it has big problems. There's no place for gravity inside this standard model of particle physics. There's also no place for dark matter. There are no dark matter particles in the standard model. Dark energy is something where we have no clue about. And then there are really, even if we disregard the problem with gravity and dark matter and dark energy, there are really problems that cannot be explained by the standard model of particle physics. There's a thing what is called baryon asymmetry. This may sound like something totally uninteresting, but in fact, it's the question, why are we here? We should not be here. According to the particles and forces in the standard model, we should not be around. There should not be enough matter in the universe to produce all the galaxies and stars and humans and animals. In fact, after the Big Bang, most of the stuff which was created in equal parts, or almost equal parts in the Big Bang, should have annihilated, because you produced matter and antimatter in equal amounts in the Big Bang, and they should have all annihilated long time ago, and there should not be enough material to form the galaxies and us. And so this is a big problem for the Standard Model, and we're still waiting for a solution to that. So we know that there is stuff missing in the Standard Model, and experiments like ours aim at looking for something, for discrepancy of a Standard Model calculation and experiment. And so people were quite hopeful that this could be the case. But still, before you make such bold claims that you have found something beyond the Standard Model, you have to look new data, look at new data and check for errors. Okay. Jan, I think it's your turn now again.
Yes. So on the scattering side, there are actually 2 experiments who provided new data. And the idea of both of them is to go to smaller Q-square, right? So that we can test this extrapolation and get maybe a better radius out. So the first one was, the first published one was, again, a measurement in Mainz by Miha. And the idea here there is to go to a smaller momentum transfer by losing some of the beam energy before the scattering. That's called initial state irradiation, where some of the energy is just taken away by a photon. And also test the radiative corrections quite well, and we can show that they are good to 1%, which is good enough for the previous measurement. So it seems that there's no problem there. And what we get out of there is a large radius, slightly smaller than what the earlier one is. But if you look at the errors, especially of the systematic error, it's so large that it cannot really rule out the smaller one. So it's compatible with both, prefers the larger radius. Right? So it didn't really help us. Then there was data from Jefferson Lab in America, in the US. It's called an experiment called PRED, and they go to a very low Q-square by going to very, very small scattering angles. Right? They actually have quite a lot of beam energy, but if you go really to a very glancing glow, you can imagine that you just transfer less and less, right? If you just really just touch it from the side. That's what they're doing, going to forward angles. And what they got out is a very small radius, actually slightly smaller than the muonic radius, but compatible with that. So that strongly prefers that small radius. And rejects the large radius. If you go at the errors, it's like 3 sigmas or so it's not as hard as the 5 sigma, but it's clearly an indication that it would like the small radius. We can now ask, does PRED actually resolve this? Was it our extrapolation or what happened? And for that, I tried to plot both of these data sets. So we start here with this form factor as a function of Q square. I divide out what is called the standard dipole. That's just some parametrization to make it a little bit more compressed. In the range, you see better what's actually happening. And this green line here is an old fit to the data pre-Mainz. This is the Mainz data with the Mainz fit, and you can see the old fit and the Mainz fit agree here on the slope, and then the Mainz fit is a little bit higher, right? It's expected. I mean, the data density on that old fit is really low compared to that. And there are some other fits, so I can fit the Mainz data and force the radius to be the muonic result. That gives you the purple curve or magenta curve. And there are theoretical predictions. There's one, for example, by Alarcon, who can also take the radius as a parameterization. And this gives the blue curve, right? So we expect the data to be on that if that would be true. And this is PRED. So PRED data on fit. And you can see they really concentrated on the low Q, but it's really hard to see any slope in there, right? Because compared to the error bars, the difference from one is negligible. But the big difference really is in the behavior at larger Q, right? So it does not fall as fast as the Mainz data or any of these predictions. And there's like 2% difference here, which doesn't sound like much. It's actually 4% then in the cross-section because of the square of the form factors. But 4% is way, way larger than any systematic errors we have on our table here. So we really don't know where that difference comes from, right? So that could be, it's still the theoretical calculations or some massive unobserved effect we didn't take care for, we didn't take out. in any of these experiments. So we need more data in the future, and there are actually many planned. So one is actually about to be published, at least the first version of that. The biggest problem in the MINDS data, or the biggest hurdle, is background. We have a cool liquid hydrogen cell, which has walls, and the beam goes through the walls, so it scatters also off the walls, and that gives you background, right? You have to subtract that. And we can now build what is called a hydrogen jet target. So it's essentially a nozzle, a lava nozzle, and you get supersonic hydrogen going through vacuum as a beam, and then it's caught in this catcher down here. And that intersects with the electron beam going right to left in this picture. So it's a point-like target, and there's no background, technically, right? In reality, there is background because you have beam halo, and that hits the nozzle and all of this, but it's different. And that's been done by Yimin Wang. He's a PhD grad student. He's now actually finished. He's now a doctor from MIT. That could come out shortly. And more in the future, there's, for example, Magix at Mesa. That's the new accelerator built in MINDS. And it's a low energy machine with high luminosity. So there we can do more tests of the electric radius, but also measure the magnetic radius at that small q square, where we actually don't know much about. So all the magnetic radius values, I think, are really not stable because they are essentially fitted from higher q square. There are some other experiments. MINDS also has a time projection chamber. It's a completely different kind of experiment where you measure, instead of the electron, you measure the recoiling proton. So you have an active target. The hydrogen gas actually also works as the detector for the proton. And that's going on now. There's the ultra low q square, which goes to even smaller q square at Tohoku University in Japan, Sendai. Pre-Red wants to do a second run with some improvements on the experiment. So there's really a lot of going on. What we don't have is precision radii for muon scattering. There are actually two experiments that will address this too, right? So we have muon spectroscopy and electron spectroscopy, but so far we only have electron scattering. So muon scattering, there are two experiments. First one is INSPYRE, which is the successor of COMPASS at CERN. We had the first test beam last year, and we have a new test plan for this year. The other one is MUSE. That's muon scattering experiment at PSI in Switzerland, the same institute Randolph measured. We took the first projection data last year, and we'll have more this year. And I want to talk about this a little bit more because that's an experiment really designed to solve this puzzle. PSI is the most powerful low energy beam for muons and pions. And we then make use of all the species available there. So we measure positrons, electrons, muons of both polarities, and pions. And we can compare the different particle species and the different charges, and that gives us really good control of all the systematics, right? We can directly see, do muons scatter differently than electrons? And is there anything like lepton universality, is that violated? And we can directly see a difference there. And with the different charges, we can control these theoretical effects quite well. It's different than the other experiments that don't have magnets. We don't have magnets there. And it's a broad beam, right? It's not like this pencil-thin electron beams you have at these accelerators. You have to produce the muons via scattering of this proton beam via this production. So it's a secondary beam. It's wide. It's 5 by 5 centimeters or so. So we have to track the incoming particles. We do that here. We have then the target inside this target chamber in vacuum. And that's, again, it's a liquid hydrogen target. And the scattered particles are then detected here going left or going right in these chambers. Star tube chambers, which we can use to track, so we know the direction of the particles, and the scintillators to actually see that there was something and to trigger off. We do some monitoring of the beam itself to control all the systematic effects. And the big challenge here is we have this combined beam, right? So we have to identify actually in the trigger whether it was an electron, a muon, or a pion, and we do that with time of flight. We know when the reaction happened in the production target, and then there's this, 20-meter pass to our target, and the particles have different speeds, right? The electrons are almost light speed, so they arrive first, and pions and muons are heavier, so they are slower. And we can measure the time from the production to our arrival to tell which particle it is. And that's how we separate them. All right, back to Arnulf.
Yes. So this is the picture that you saw, and Jan told you about the wonderful projects that have been also motivated by this discrepancy in the electron scattering and muon scattering community. Of course, there's also new projects in the precision spectroscopy of hydrogen, namely to try and check if this world data on hydrogen is really correct, or maybe there was some problem there. First, yes, we also can determine the proton radius from our Munich deuterium, which is in agreement with a small proton radius. And then in like 5 years ago or so, the first measurement came out of the new class of experiments using normal hydrogen. And lo and behold, it agreed with the small charge radius of the proton, right? So in contradicting directly this data point here with the world data, so something must have gone wrong here if this point is correct. Then a year later, guys from Paris remeasured something in hydrogen, and they got the large radius again. But then Toronto, they measured the lamp shift and the classical lamp shift in hydrogen, and they came again up with the small radius, and we again did yet another measurement in, sorry, wrong way. In Garching, here you see the P-rad point, which is in the small radius, and a new measurement of the same transition in hydrogen as the one from Paris is here from Garching, which was published end of 2020. It's also on the small side. So there's a big problem. It seems that if this value is correct, then there must have been some systematics in here and in there from the hydrogen side, which is not showing up in these more recent measurements. And maybe the electron scattering also has something to learn from the low Q square, as Jan explained to you. So we have to keep looking and identifying the problems, because just putting up a new point on this table is not really helping. One would have to find out if there's a problem with these new measurements, or where the problem with the old measurements was, or maybe still people looking for problems in our muonic value. And I think it's again Jan, right? Or are you done? Then I finish.
I have only one more slide. So it's
one more
just
slide.
Okay.
Slide.
So on the scattering side, right, there are so many experiments on the way which really highlight or try to eliminate this puzzle from different directions. So we hopefully can figure out what's going on. But just one remark here. It's really rare that you have different fields of physics overlap in this way, that we can really measure the same thing in these different ways. And this is always really precious, because you can always learn something, right? So even if it turns out this was only just measurement errors in all of these old measurements, and it's okay, we have a new value, which, I mean, I think it's a 6 sigma shift in Rydberg constant as well, right? So it's a big thing anyway. But even if you just learn how to do the experiments better, right, we would not have learned this if there would not have been this overlap. So thank you for listening. If you have questions, write them in the chat. I think you have some time to.
I also have one more slide with an advertisement of an article that Jan and I wrote. Actually, it's already a long time ago, Jan. You know this, right?
Yeah, I know.
We wrote an article for Scientific American, actually, and it was in all of the issues. You can read it in any language you like, I guess. I
think there was one we put it in.
Sorry?
There was one edition.
Yeah. So the question is still around: is it a freaky measurement error, or? But if you can read about this story of the two of us and the proton in this article. And as Jan said, it's always nice to have complementary measurements, because in the end you learn a lot from every discrepancy, from every mistake you make. And now I would also like to thank you. This is my group at PSI, the Proton Size Investigators, who did this measurement a long time ago, and we've been continuing with this. We've now measured the helium charge radius, helium nuclear charge radius, and we're aiming at tritium and other nuclei. So there's a lot of things to be measured in the near future. And we're also looking at the magnetic radius of the proton at PSI. So this is the list of cover pages on this proton problem in the Scientific American. And if you have questions, please feel free to ask them.
I think there was actually one question about the Rydberg constant. You might want to answer.
So, okay, first of all, thank you very much, Jan and Randolph, for this extremely interesting talk. A bit complicated, but of course, this is the argument. So, yes, unfortunately, we ran a bit out of time because in 10 minutes we have the second seminar. But yes, maybe you can ask Paul's questions. He asked for the role of the Rydberg constant in the equation.
Yeah, so when you do the calculations, you usually go to atomic units. You put a bunch of constants, make them 1, and then you can calculate them and don't have to carry these constants with you. And in the end, you do the measurements in SI units, which means you're working with the second or frequency in hertz, which is the inverse of a second. And to convert from these atomic units to SI units, you need this conversion constant, because these SI units are basically determined by arbitrary numbers, right? It used to be the circumference of the Earth which defined the meter, and it was the day length which defined the second, which is not a universal number, right? Now we've put it into the speed of light, which is of course universal, but the length of a meter is still related to the diameter of the Earth. And also the second, which used to be a day length, is now related to some cesium frequency, but it's also not something very fundamental. So the numerical values of these fundamental constants come into play at some point. And these are coming into the Rydberg constant, and the Rydberg constant defines the energy scale of an atom. And that's how they enter these equations. In the end, it's just our historic traditional way of measuring units compared to the clean way of calculating them in atomic units.
Great. So if you are really short, maybe we can have another one. The other one is, can you use this method or other methods to measure the radius of other particles?
Yes. So we are measuring all the nuclei, both in electron scattering and atomic physics spectroscopy. So proton, deuteron, helium-3, helium-4, lithium, beryllium, what you name it. Other particles like the pion or so on is more difficult. That's more the realm of scattering experiments. You can also measure the sizes of unstable particles, other compound particles.
Yeah, there are many measurements on all of these elements in scattering.
So let me thank you again very much for this. Unfortunately, we had to stop because in 8 minutes we have the second webinar. So thank you, and for the guys, for the students, girls and boys, you can stay here on this playlist, or you can click on the link that you see on the chat. Thank you again, and
thank you.
See you next.
Bye bye.
Bye.
Ciao.